Hi, welcome back to my channel. So last time we obtained this expression and evaluated the denominator somewhat explicitly. So next we have to consider the numerator. So let's copy it. Yeah, why are we considering such an expression? Because our thing was the integral over a product of intervals where I is the interval of size square root of log r, and we multiply this with the Fourier transform of something. The variable is psi I k. So we have been reduced to computing this value. So we use the fact that this zeta function has a pole of order 1 at 1. Namely, when epsilon is a small value, this is close to residue divided by epsilon. And therefore, we will consider this kind of thing. So zeta 1 plus this strange fraction 2 plus something divided by log r. So this is by the formula residue times log r divided by 2 plus, and then since this inverse can be confusing, let's compute the latter ones in advance. So 1 plus xi. So if I take the inverse here, this is close to, yeah. So if I use this on our expression, we will get yeah. So these are coefficients that we can bring in front of the expression. So let me see this thing. So this thing will be residue times log r divided by 2 plus I times 1 plus I psi 1 divided by residue times log r, and the second variable. And here we have a cancellation. So if I take the product, we will get residue log r to the power of m and the product of So we multiply this by chi hat and integrate. So this gives us, and let's ignore the coefficients. So what we have to compute is the integral over this of this is what we have to compute, and this is a Fubini type integration, so this splits into a product of integrals. I could have copied the previous expression just electronically. So it becomes a product of integrals. And now I can modify the domain of integration back to the entire space up to small error. So this is interesting because in previous parts I have used the fact that we are on bounded interval. Because we have used the fact that this is small. This part. Because our variables are in a bounded domain. So certainly some of the things we have been doing are only valid on bounded intervals. But now we are changing the domain back to the entire space. Then this can be computed. So this equals to this thing. For an algebraist like me, it is impossible to see this expression and identify it as this thing. But once you are told the answer, it's relatively easy because I can start with this expression and try to deduce this expression. So let's do that. Proof of the claim. So recall by definition that by Fourier transform that this is chi hat. By the definition of chi hat, I have and I take the derivative in x of both sides, and by some calculus I can simply differentiate this part. So minus 1 minus I psi, and I take the square. Then the right hand side becomes an integral in two variables by Fubini type identity. The negative sign cancels out. And if I take the product, this part becomes the sum. looking similar. And lastly, I integrate in x. The left-hand side becomes the claimed expression, and in the right-hand side, so again, I'm allowed to simply integrate this part. So these parts don't change. And if I integrate this, so this comes as the denominator. So I get this fraction. And let's not forget the minus sign. 0 to infinity. Right. And this thing is, so when x is the infinity, it's 0, minus when x is 0, the value is minus 1, so it's 1, so we can simply ignore it. And we end up with what we wanted. Yeah, so this shows the claim. And this shows the theorem, actually. Yeah, because basically then we have computed everything. So this shows the claim, and then this has been computed, so there's nothing to compute further. So let me quickly give you the summary of the computation, summary of the proof of the theorem.